Hi, in this video we are going to talk about the concrete implementation of the Untitled problem. So let's get started. First of all, this app.java, this is the class from which we are going to test our algorithm. In the constants, it has a private constructor. Why is it good? Because you will not able to instantiate it. We just try to store static final, so constant variable in this class. And the Untitled is the one we are going to focus. So here we have a solution matrix. We are going to represent the chessboard with a two-dimensional array or with a matrix. And as we have discussed in the theoretical section, we are going, if we are standing on a given cell, we have 8 possible moves. Okay, if we are standing on the edges or for example in the corners, then not 8 moves. Okay, we have to check whether it is a valid move. But where there are 1, 2, 3, 4, 5, 6, 7, 8 moves. For the x-axis and y-axis, two-dimensional plane, we will have 2 coordinates to define a move. Okay, so it's going to have as many rows as the board size and as many columns as the board size. So it is a quadratic matrix. We initialize the board. We get every cell value will be the minimum value, integer that minimum value. It's good because we try to track whether we have already been visited that given cell or not. We are going to know that if it's the integer, that minimum value, it means that we haven't visited it. Okay, then the solve Untitled problem, it is quite the same. The backtracking algorithm, as you may recall, for example, for the coloring problem implementation or the Hamiltonian cycle implementation, we are doing quite the same. The first move was we start at the left corner, so that's why the 0, 0 index is the 0. This is the starting point. So if we are not able to solve the problem, if it's going to return false, then no feasible solution found and return. If we find something, then we show the results. So the solved problem is going to get the x coordinates, y coordinates, so this. And because we have already settled the 0th index, we start at 1. This is the step count. Because if we solve, if I run it, the step count is going to denote that this is the 0 count step. This is the first step. This is the second step. So that's why we use this step count. It's quite the same if the step count is equal to the board size times board size. So we have already considered every possibilities. It means that we have solved our problem. Return true, and because it's returned true, it's not false. We just saw the solution. Anyways, we iterate through the board. We define new steps with new x, new y's, and if it's a valid move, which means a move is valid if it's on the board as far as the x coordinates are concerned. It is on the board as the y coordinates are concerned. So if we are out of the board, we return false, both the x and y coordinates. And if it's not the mean value, it means that we have already visited it. If we have already been there, it's not going to be a valid solution. We are looking for cells that has a minimum value. So we return false if we have already visited it, and anyways, we return true. So we know that it is a valid field. We haven't visited it yet, and it's inside the chessboard. Then we set the step count to this new x and y, and try to solve this problem for the next x and next y coordinates, and of course we have to increment the step count. And if it's true, it means that it is a good solution. We keep going. If it's false, that means that we have to remove this solution, and that's why we backtrack. That's why the algorithm get the name. And we set it back to the minimum value because we come to the conclusion that, okay, this is not a good solution. We try going in a way, and we come to the conclusion that in this situation, our problem is not feasible. Maybe if we backtrack and go another way, it's going to be feasible. So that's why we have to use it. But we have to use the same approach for coloring problem and for Hamiltonian problem. We have to check whether it is a valid move. If it's a valid move, we have to check whether for the next item, for the next step, Is it valid? Is it solvable problem? If it's true, then okay, we keep going. If it's not, then we have to backtrack. And of course, if it's not, we return false. And of course, the show solution, I think, is pretty straightforward. Iterate through the board and show the... So if I run it, it is going to solve our problem. Let's see, for example, when it is not feasible. When we try to solve the problem for a 4x4 matrix or chessboard, there is no feasible solution. What about 7x7? It is going to be feasible. First step, second step, whereas the third step, fourth step, and so on. So it is feasible. So that's all about the Nitor implementation. Thanks for watching.